photolithography. In photolithography, we follow two processes: photographic mask and photo etching. Let's start with photographic mask. So what we do is, on top of the prepared wafer, after applying the SaO2 layer, on top of that, we'll have to draw the structure of IC. Draw the structure of IC in sense the small components, right? So what we do is we use computerized softwares to draw that, and we magnify it to about 500 times, and then we draw the structure. After drawing that structure, we put it on this sheet. We put it on this sheet, and then we paste it on top of the SiO2 layer. After that, we use this specialized instrument to remove the non-useful parts, right? So we make the design, we put it on the sheet, we remove the non-useful part. After that, what we do, the part where we remove the sticker will be exposed, right? We'll expose the SiO2 layer underneath it. So what we do a process called as photo etching to remove it. What is photo etching? Etching is removing, and using light to remove is photo etching, right? You can understand it much better with this video, I mean with this image. uh, this is the substrate, this is the deposited film. After that, on top of that, we use something called as photoresist. Photoresist is a layer adder that will not that will not let light to fall on it, on the inside part, and affect it. So we coat the layer with photoresist, or in this case let's consider as a wood. And on top of that, we are using the mask. Mask is the diagram that we have drawn and put it on that sheet. And then on that sheet we have already removed, right? So this is the region that is removed. So when we paste it, and when we pass light through them, the light will come and fall on this region, right? So this light has the ability to etch away this part, that is photo etching, right? So we here they have called it as a development. The reason is because this region is etched, but this region will look like it has been etched, right? Then after that we further etch and remove all this region, the SiO2 region. First we remove the photoresist, now we have removed the SiO2 region also. So now this substrate is exposed, right? Now and then we remove the photoresist, right? And so how do we make this process? We use photo etching, and for photo etching we use either ultraviolet or X-ray, right? And this etching can be in two way. One is wet, the other one is dry process. When you use chemical, it becomes wet, so we call it as wet process. If I use X-ray or plasma or something like that, then it becomes dry process, right? Yeah, we can use ultraviolet or X-ray. Mostly we use ultraviolet. The reason is because X-ray is costly, it takes, and it's meant only for small devices, right? Then moving on, diffusion. See, we have seen that this is what has been created. Now this is p-type material, and so is these, but we need this to be n-type. Only if it is n-type, you can make a diode out of it, or you can make a transistor out of it, right? So to do that, what we're doing is we are diffusing some impurities into it. So how do we do it? We take a boat, not literally this boat, something like of the shape, and then we put this wafers, around 20 to 30 wafers on it, and then we we put it in high temperature of about 1000 degrees Celsius, right? Then it will be in the boat under 1000 degrees Celsius. Then we will blow some boron oxide or boron chloride, phosphorus pentoxide, or this kind of chemicals. So how do we blow? Or this will be in gaseous state. We use this dry oxygen and nitrogen gas, and we blow using this. So this will act like a carrier. This will carry these chemicals, and it will pass to the wafers. So this wafers will absorb this particles, and it will become either N type or P type. If you blow this boron and boron pentoxide, it will become N type. If you blow phosphorus pentoxide or phosphorus oxychloride, this will become P type. Right. So that is what diffusion is. But the problem with the diffusion is, let's consider. Let me draw it Yeah, okay. This is the substrate. In this substrate, this region was developed, right? So this should be the, I want to make this n to be n region. Now if I diffuse, what happens in diffusion is the diffusion will take place like this. Slowly it will be diffusion. Even if I diffuse it to the maximum, this region will not get diffused, right? So to overcome that issue, we started using ion implantation. So in ion implantation, what we do is uh, we implant ions in this direction, so it will come forward, it will come forward. So it will scan from right to bottom, from top to, I mean from right to left, from top to bottom. So how does, in what condition they do it? So we subject the wafers to vacuum and then we do the scanning at very high temperature of about 20 to 250 kilovolt. It's very high. So as a result of that, what happens? Ions will get penetrated and the lateral spreading happens and you get a perfect doping, right? And then see, now we have structure form. Let's consider the same like this. Let's consider this as P. Now we have diffused N here, another N here, another N here. Now you want this to be NP diode and you want this to be NPN transistor. So how will you differentiate this? How will you isolate this? So in this case, you can isolate either using dielectric or using PN junction itself. How you see, if you insert some dielectric material, some insulating material, it will be isolated, or you can inject a small end layer, right? If you inject n layer, what will happen? This will become P, this will become N. So in this region, the region where P and N is joined, or in this region, so P is holes, this is minus, holes, electrons, holes, electron. So what is happening here? A depletion layer is formed. So when depletion layer is formed, will there be any transfer of electrons or holes? No, there will not be any transfer. We are also not going to give any barrier potential. So this will remain as a depletion layer. So that forms a isolation, right? So proceeding further, metallization. See, we have formed this layers, right? We have formed this N, P, N, P, N, everything is formed. In certain cases, you need this N to be connected with this N, this P to be connected with this N. So this contact, how will you make? So to make that contact, we use metallization, right? So this is the 3D way of this metallization. Anyway, I'll have another video prepared and explain you the 3D structure so you can understand this better. And what metal we use here for metallization? We use aluminum because it is a very good conductor and it can easily be used in vacuum deposition. It bonds very well with as a silicon and so on, so right. And after all this being done, we do packaging process. We assemble and we package. Mostly we use uh, dual inline package, or other case we also use TO5 package. In very rare case we use ceramic flat, right? So the one IC741 that we study are actually dual inline, whereas the MOSFET mostly comes in TO5 form. MOSFET are mostly the BJTs, they come in this, right? So this is with respect to IC fabrication. I will show a image that will help you understand how it looks in microscope. So this is the image or the drawing that is drawn on IC. This is a photo taken in our microbiology pathology lab, right? So this is how small the diagram will, I mean, the circuit will look inside the IC. So with this, I'm concluding the session. So